This is the full from scratch with explanations, pretty much unedited version of the liquid fluid simulation tutorial. We'll do some more things here as well, not just what you saw on YouTube, but we'll deal with obstacles and additional sub-steps so that the simulation is more accurate. When you have, for example, high velocities and some obstacles, it will come very handy in those cases. Let's delete this cube here, or actually we can get this back. And let's add a new window here that is for our geometry nodes, because that's what we're gonna do, right? And let's add the simulation grid. In that sense, it's very similar to YouTube. And we have to use the resolution. So what the grid represents is, for example, if you have like 10 times 10 grid, it represents each point here, what water or the fluid is doing, you know, in the average area of like that. This is what this one point in the center here is representing, and every other point as well, because we couldn't, like, you know, simulate every last molecule of this fluid field, so that's why we make this approximation. This resolution of 10 is a little bit too little, so let's add like maybe 40. So now we have a decent amount of detail, and let's add the velocity field on the surface here. So I'm going to take a store named attribute, and why I'm using the store named attribute is that the velocity field is something that is stored on each one of those points here, and it's kind of like a variable. If you have done some programming, an attribute is like a variable, and this can change. It's just a packet of data that is on each point here. So if I, for example, so to make this vector and just store the value of 1, 2, and 3 on each point, I'm going to call this the velocity. And if I now open up the spreadsheet, you can see that here I have different views of visualizing this, but I also have, you know, on each point a velocity attribute called 1, 2, 3, 1, 2, 3, 1, 2, 3, because it's the same on every point. If I add another attribute, like let's say F, then I have this here. So this is how you can preview or visualize your attributes. But we're not interested in 1, 2, 3 on every single point, but instead we want to have something meaningful. So let's take, for example, let's make the same vector field that is pointing to the right, as I saw on YouTube. So I'm going to take a position, and I want to eliminate the right side of the grid. And I could do this actually in many ways. I don't have to use the position. For that, well, since I'm making the grid in geometry nodes, I actually cannot access those points manually. But if this was a manual thing, I could, for example, you know, select those points here, and I could store a vertex group here that is called a group, for example, assigned here. And now if I preview my cube, and I can take the named attribute here and preview the group attribute, you can see this side here is white because this has been selected. So the position is not, you know, the only thing to do this, only way to do this, but since in geometry node selection currently is a bit cumbersome, this is how we can do this. So I'm going to separate the position into the different channels, X, Y, and Z. And if the X is larger than something, than 0, then the right side of the grid will be selected, and the left side won't be. So I'm going to take a compare node, which gives me a Boolean attribute, true or false, based on this condition here. And the condition is, if the X input is greater than 0, then give me true. If not, give me false. So I have 1 true here and false I have here. And now I want to store on this side my attribute. So I'm going to just plug this into the selection, and I'm going to view the velocity attribute that I'm currently storing, which is fully white, and that's because it's not fully white, because the values are so large. I'm going to put it to 0, and let's make it like 0. Let's make it 1. So this is 1 meter per second. So this means when 1 second passes, this field should move to 1 meter, which is obviously too fast. So let's make it a little bit slower. Let's make it 0.2 meters per second. So I'm gonna put here 0.2, and now it should move. So let's make it move. For that, we have to somehow, well, actually, we should be visualizing this attribute for that. For that, we should think how we can make this attribute move. So if I have those points here, and I'm gonna turn off this X-ray here so that we can see this a bit more clearly. If I have, for example, this point here, and I know its value has to move based on the velocity. So we want to currently move the velocity itself. But let's say we had like different values here. We wanted to move with the velocity, doesn't matter. We currently just want to move the velocity. Whatever we have here, we have to move it by the velocity, which is 0.2 meters. So from here, we should put, the value should be there. So we should put the value around here. Like that. How do we do this? Well, if you would like to do this, well, first you have to know what your value is, which is easy. We just read it in from here. And then where are you going to put this? Well, for about here, which is 0.2 meters. But we don't have any points here. So obviously we cannot do this. We can't write this exactly here. Instead, there should be like an average of, let's say around 70% here and maybe 10% here. Okay, very nice. But what if we had, for example, some other points coming in from here, like here? Then we should, okay, we want to write this here. So some contribution goes here, some contribution goes here, here, and here. This is possible to do in general with computers, in programming, using a programming language, but with geometry nodes it's not possible, and for a very good reason. Because geometry nodes only operates on the current point. So what you can do is you can do operations on a certain point at a time. So for example, if I want to do operations on this point, what I can do is I can take data from other points. I can do all sorts of stuff like that. But what I cannot do is that I cannot operate on this point and then write this data to another point. I can't do this. For that, I have to set this logic on this point to take the values from here. I can't do this the other way. So I can't send data anywhere. I can only read in. And the reason behind that is multi-threading, I believe, multi-threading. Because if you have two, velocities happening at the same time in the same location, this creates some problems with multi-threaded CPUs. You can do this with only one thread at a time, which means it's gonna do all the points like that, and it's gonna be pretty slow, because if you have like 10 cores, you can do this 10 times faster. So let's do this the other way around. As you remember, we cannot write to anywhere, but we can read in. So instead of that, let's do the inverse. So which value should be here instead? So let's turn it around, and we should get the value from here. That, can I have right here? We should get the value from here to be there. And this can be done because we are reading in data from somewhere and we are operating on this point here. But still, if I get the value from here, I should get something from here, something from here, something from here. So basically the average contribution on this face at this point. And for that, I luckily have a node in Blender, which is called sample nearest surface. So what this does is that it gives me a value like a float, integer, vector, whatever, and it gives me the average value at the face. So for example, if I have a value like maybe I have 0 here, I have 0 here, I have 1 here, I have 0 here, then I can move around here and I can get different average values, which is going to be, for example, 0 here, but it's going to be 1 here, maybe 0.5 here, and so on. And this is what this node gives me. So let's use this node to sample the nearest surface from which from which geometry are we interested in doing that? Of course, from our velocity grid. So I'm going to put this here, and I'm going to preview the value. Currently, we don't see anything because we are not sampling any values. So let's sample the velocity, of course, and we see the exact same thing. Control Shift click on those two values; they are the same, which is very logical because currently what it does is if this thing here isn't connected, it is gonna use the position node like that. So it's gonna for each point it's gonna start, for example, here, and it's gonna find the nearest value at the same location because we are using the same position of that certain point in context. So we should somehow use a different position. So let's just use vector math here and use a subtraction node. So for that, let's do, for example, so that all the points, like this point, for example, reads in a value from here in this direction. So if you put like 0.1 here, and I'm gonna delete everything for a moment. I'm gonna disable this, and let's measure. So 0.1 is around that much. So if I enable this, you know, this point that is here, it's going to take in a value from here because I'm adding something to its position. So we should do the other way around. We should subtract the velocity from it because, and I'm going to do it so that it's more clear. So if you subtract the velocity, it will go back by the amount of the velocity to somewhere here and take the black value here, and this value will take a red one from here, and this one will take a black value, and so on. So it moves to the right, but it does so per one frame, but our velocity is per second. So we should do something about this. So currently it did this just, you know, as I turned it on, it did this in one, you know, instant. But I think it's, you know, clearer if we first make it animated and then deal with the speed of those things. So let's do this on every frame, because currently if we play this animation, nothing is happening really. I'm gonna make it to be 60 frames per second to be more smooth, more fluid, and we should somehow find a way to do this on every frame. For that we can use the simulation zone. And the simulation zone is just essentially a loop. Essentially a loop very similar to the repeat zone, in a sense that, you know, with the repeat zone you can manually control how many times you want to do this. I mean, for example, if you were to do so, see in time frame into the iterations, then it would give you the exact same result, because on every frame that you do things, you just iterate this once more, what's inside. And the simulation input and output functions so that you take in what's before, and then you repeat and repeat and repeat and repeat this, and you spit it out, and you execute those things here once also. So here we do things once, here we do things infinite amount of times, and here we do things once again. So let's put in this thing here. Let's do like that. And what do we do next? It's a good question, right? Because we cannot just plug this here, of course. It needs to have a geometry output. We have to store this. So let's store the named attribute. And as which attribute? If we were to just store this as an attribute called carrot, then it doesn't help us. Why doesn't it help us? If we preview the velocity attribute, it doesn't change. If you preview the carrot attribute, it is changed, but I mean, every frame it just reads in the, it just takes, you know, the velocity attribute, moves it, stores it as carrot, and nothing really accumulates over time. So let's do so that we take in the velocity, we move the velocity by the velocity, and store this as the velocity, and then we do it again and again and again. And this means that we are moving the velocity constantly. Let's see if this works. Let's take the velocity attribute, and if we play this, it disappears very fast. Not 0.2 meters per second, definitely, because 1 second is currently 60 frames. So here it should be only around here, but it definitely isn't. So we need a way to make this frame rate independent, and for that we need a time step. So let's say you have an animation 1 frame per second, and you're doing this, and you have a velocity of 1 meter per second. So this is your frame, and you have this velocity here. So 1 frame per second. Actually, I think I'm gonna take my graphics tablet because it's gonna no, I'm actually not gonna take this. It's kind of a it's kind of cumbersome to write with, so I'm gonna try my best with the mouse. FPS kind of works, you know. You understand what's written here. 1 frame per second, and during 1 frame, this okay, this is 1 frame, and this is equal to 1 second. And if you have a speed of 1 meter per second, 1 meter per second, this means during 1 frame I can easily just execute this velocity. But what if I have a speed of animation of 2 frames per second? Then if I now execute you know, the same velocity, I have, you know, in 1 second I now have 2 frames. So I have 1 frame, another frame, maybe you like those F's more. So I have 2 frames, and the second is still the same. It's 1 second. And now if I do in this frame the same velocity, and here again the same velocity, I get twice the speed. What I should do is that I should multiply the velocities with 1 divided by 2, which is 0.5, and I get to the same location, but with just twice the amount of frames. And for example, if I have like 2000 frames, let's say, obviously I have like a lot of those frames here, and I have to make very small increments of this velocity so that in the end I get to the same location. So here I should do 1 divided by 1 times the velocity. Here I should do 1 divided by 2, because I have 2 frames in 1 second, times the velocity, and here I should do 1 divided by 2000, super ugly, times the velocity. This is how the time step works. And let's do this. So this thing here in theory should give us the time step. So let's see this. If I put a viewer here, why can't I view this? Okay, let's see what the viewer gives us. It's a plain 0, and for some reason just this value doesn't work for me, and I haven't understood why yet, although it should give you automatically 1 divided by 60 all the time. So let's make this, you know, ourselves. Let's store a named attribute that is called delta time. Delta is the change in physics, for it is written like that, like a small delta. Delta time is 1 divided by 60. We could do clearly just that. If you know that we're never going to change our frame rate, this would be okay. But maybe we are changing our frame rate. So I'm going to group this, and I'm going to take away those selections, names, and values here. And instead, I'm going to add a math node and set this to a division. And I'm going to do 1 divided by the frame rate, which I'm going to take in from here. I'm going to set this to be an integer because the frame is a full number. I can't make, you know, 7.2 frames per second, or can I? No, I can't. These are always full numbers. Although the base seems to be working, but anyways, 60 frames per second. I'm gonna call this FPS. Minimum would be 0 or 1 FPS, to be honest. I'm gonna make the default 60, and maximum could be whatever, if you're a fan of high frame rates. And I'm gonna put this here. So now I have 1 divided by 60 is my delta time, and I'm going to call this time step, and let's put the FPS to 60. And now I can just take a stored attribute called delta t, and I can scale the velocity with the delta t. So let's see if this thing is now moving where it should. Let's measure from the center. Where is my measure? Let's measure 0.2 meters. So at 60 frames, it should be there. And if we do like that, we can see it kind of has moved there. But since it's, you know, it's kind of blurry, and that's okay, that's normal, because it's like ink in water, which is exactly how, you know, fluids behave. So if it's, for example, going here and then here and then here, you don't have points here, so it's kind of doing this averaging out between different elements, and this is why it works like that. So it's okay, trust me. The fact that it diffuses like that, diffusion is the correct term for this behavior. And now it is moving, and the very important thing to do when you are doing, you know, kind of large projects, like I would say this fluid simulation is, you know, if you don't group nodes, it gets kind of, you get a lot of nodes here. So let's group what we have here into this one thing, and let's name things nicely so that we can understand what is actually happening in our node tree. So I'm going to call this geometry, output also geometry, but the more important thing is to understand and think ahead a little bit. Of course, if you are just doing this for the first time and experimenting, you don't know all that. But I know that we are going to use this node group later on to advect some colors with the velocity or any other attributes and move them with velocity. So let's make this node group reusable so that we can not only move the velocity here, but any other attribute. So I'm going to drag in the name here, and now I can call this just attribute to move, and I can drag it also here because I don't want an attribute called color, for example, to be stored as velocity. Instead, I want this to be stored as a color. So this is how this node group is reusable now. But I always want to move the attributes with the velocity, so this is okay here. Delta time, everything seems to be correct, and let's call this node group advect. And now we have our velocity field moving, which is very good and a good start for the liquid simulation. But let's add a better fluid field to understand this, which is of course a noise texture, as we did on YouTube. I'm gonna make this can be 3-dimensional, doesn't matter, and I'm gonna preview how my velocity looks like. I'm gonna take the velocity and preview this. Looks like that. I'm gonna remove the selection. I'm gonna keep it around just in case. And I mean, this looks okay, but if you know how the noise currently works, is that, you know, you see this like a gizmo here in the center, right? The noise currently gives you the exact same values as a coincidence. Gives you something. Oh, I can't understand what's happening here. It gives you something, you know, for some reason it just starts to move. Okay, it gives you some positive things on the Y, positive things on the Z and on the X. So in the end it moves like up there, like that, because all the axes are positive. But what we should do is that we should remove the, first of course, the Z axis, because it's just useless. We are doing a 2-dimensional simulation, so there is no way that our fluid is pointing up from here. So let's first remove this. I'm gonna do multiplication, and I'm gonna multiply all the other things with the Z with the 0, and just keep the other axes. But now, you know, it is moving to the right side, which it for some reason isn't doing. Okay, I'm back. There was a Blender bug. For some reason the simulation just didn't work anymore, so I just kind of had to fiddle around with the parameters, and they started to work eventually, but I really couldn't understand what the problem was. Anyways, the velocity field is now moving, advecting itself, but doing so only in one direction. And that's because we have positive y and x values. We don't have anything negative. So let's subtract something to make the field negative, like 0.5 for example. And now it is, those black areas are negative. So for example, if I would add an absolute node back, it would look like that. So the negative areas are pointing, positive are here, negative are in all sorts of other directions. So that's why it should be equally distributed, not just moving into one position. And you see it works and we get those lines. That's because the velocity is moving, but it actually isn't taking into account the pressure that is happening, that it's actually supposed to be a fluid. It's supposed to flow, not to go when there is too much pressure and clashing, like for example in this area, negative side going there, positive side going there. They should actually be more like maybe that and start to swirl here and so on. So we should somehow enforce these rules. And to do this, what we need is divergence and pressure, and then fix the vectors by the pressure. So what is divergence? Divergence is the out and inflow. I think I explained this pretty well on YouTube. If you want to, you can rewatch those animations. Because I think I can't do any better than that. Although I can try. So if you have one cell, let's actually use the cells we have. So you have a cell, for example, here, and you have some inflow. So these neighbors are for outflow. The ones down here are for inflow. Can be any neighbors actually, but you can't just have all neighbors for the inflow, because you have two directions. You have x direction, you have the y direction. So obviously you have in any direction water can flow in or it can flow out, unless it's like an obstacle or something, but it can do this. So you need one inflow, one outflow per each direction. And then if we, for example, the divergence is the net outflow. So if a lot is flowing out from here, then it tells us that the divergence is positive. If there is a lot flowing in, the net outflow is negative, then it is the divergence is also negative, because it shows us this. So how it works is that you let's first do this on the y, for example. Actually those arrows here, they are just, we can keep this in mind, that here we have out, and here we have in and in. Maybe I'm gonna do out, unless otherwise it's gonna look like a 0. And each point has their velocity. So for example, the velocities might be like, I don't know, that. And each velocity vector has x and y components. And if you're doing only on the x, we are interested in the x components. So the x component of this velocity, I would say something really short, and this velocity is something maybe longer. So let's do so that those values, for the sake of demonstration, I think these might be like 4, and this is maybe 1. Of course, more like 2 and 1 maybe. So if you want to know how much is flowing out, you have to do outflow minus inflow, how much outflow is left. So it's like, salary and expenses. We want to know the net amount of money left in the end of the month, for example. Then you're going to do out minus in. So net outflow. So you want to know your net expenses. Then you do expenses minus income. And if you do, for example, earn like 2,000 euros per month, and your expenses are like 1,500, you do expenses minus income, 1,500 minus 2,000, which is minus 500. So your net expenses are minus 500, which means you have this surplus of money at the end of month. You have more money than you spend. You're more than you spend, which is great, right? And here we do 4 minus 1, so we do 4 minus 1, which is 3, out minus in. And here, let's say these numbers are just like, here we could also have minuses. Let's say we have minus 3 going out, because the velocity can be whatever, and we have -3 coming in. Now it is a bit more complicated, isn't this so? But just remember the rule, out minus in. So we do -3 minus -3, which is -3 minus -3, and actually it should have brackets, which is, you know, those two minuses actually turn into a plus, so it's -3 plus 3, and this whole thing is equal to a fat 0. So we have 3 on the x, 0 on the y as net outflow. However, this is per 2 points. This is how much is the average, you know, per those 2 cells, but we actually need for the middle one here, so we divide this with 2. 3 divided by 2 is 1.5. If this seems a bit counterintuitive for you, what you can do is that you can take into account also the center velocity. And let's say the center velocity is like 0, 0. And if you do it like that, so that you do 4 out minus in, so 4 minus 0, 4 minus 0, which is 4, and you do 0 minus 1, because for this cell here, this one is the outflow. So you do here 0 minus 1, 0 minus 1, which is -1. Then you get like the flow for this segment and for this segment. So here it's 4, and here it is -1. And now if you want to get the center one, the average one, you just find the average of those two, which is 4 plus -1, 4 minus 1, which is, surprise, surprise, 3, divided with 2 is 1.5. So we get the exact same answer, just the upper one calculating for every pipe here is a bit more work, so we just do this out, in, divided by 2. Okay, we have the formula, so let's find this, and let's do this. I'm going to delete this, and for that we need the neighbors for each point. So let's first find the neighbors, and for that I'm going to use first the logic for finding neighbors. Keep the divergence logic in your head. You can rewatch this, of course, afterwards. I just deleted this to be more proper here. And if you want to find the neighbors for, let's find another point so that it's more interesting, although they are all the same. So if you want to find the neighbor for this point, we first have to know how far away is the neighbor. Where should I look at? I can find, if you want to know your neighbors, if you're living in a flat, for example, you want to know who's left and right from you, down and up from you, what do? Well, first, like literally, think what would you do if you were to find the neighbors that you have in this flat house. I would first go into the direction of my left neighbor, and I would find the closest flat in this direction, because the closest flat apartment in this direction will be my neighbor. So we need the direction left, and the closest point we can find in this direction is our left, in this case right neighbor. And with all the other things as well. I mean, if you want to find the neighbor down, I just have to go down by this direction, and the closest apartment I find is my neighbor. So let's first find what is the direction. I mean, the direction is pretty simple. It's just a vector. And I mean, if I do x like that, this is the correct direction, although it's quite long. I mean, x on 1 would be like super long. But let's do so that we find the exact distance, because we know how far the neighbor is. It's a grid, and all the edges have the same length. So we can do this. We can make like an analytical calculation. So we have, we know like 1 meter and 60 vertices, whatever. But I mean, it's a bit cumbersome, and I just like to make an automatic way for this, which is with the edge vertices node, and this gives me for each edge. For example, for this edge right here, it gives me the position, index and position of these vertices. Position is just for the convenience, because we can get everything we want from the index. But let's use evaluate what am I talking here? We already have the positions. So now that we know the position between those vertices, we can find the distance between those vertices, which can be done actually pretty simply with just a subtraction node. So we have vector math, and we can find the distance, or we can just use distance, like that, distance between those two points here, which is internally the same thing as if you were using a subtraction node, like that, and after, what happens? And after that, the length, so this distance node does the exact same thing in a shorter way. So now if we preview this on the surface, we see that. We get the value of, on each vertex. For some reason we still can't see the value, which is a bit weird. On each edge, sorry, it's an edge attribute, of course. We are looking at the edge length. It is 0.017, which if we measure, I think we should get kind of the same number, 0.017, yeah, kind of something like that. So if we know that, we just now have to, store this value on those points. So let's use a store named attribute, and let's store on the grid. I'm gonna do like that, so that, sorry, I'm gonna delete this area from here, and I'm gonna move them down here, make a little tidy up, and now we can store this as the edge length attribute that we can call edge length. Nice. Let's preview this attribute now, because we want to be sure it is displayed correctly. And if we now preview this, it looks okay, but I'm looking actually for a problem that is happening here. And the problem is, I think it shows this. No, it still seems to work fine, because sometimes it stores the, yeah, exactly, this is what I'm talking about. You see, we are looking at this attribute edge length on each point, and it shows us different numbers. So if we were to visualize this on the edge, it tells us 0.017 on each vertex. If we set this to the vertex mode, we've been storing this on each point, it is like 0.013, and that's because of the interpolation. Like you have points, and you want to store this attribute on those points. It does some kind of an interpolation. I am currently looking into the full logic, so I can't tell you like exactly mathematical what it's doing, but the thing is, it's evaluating this attribute in a wrong way. So we have to use evaluate on domain, and if we now preview this and we set this, we force geometry nodes to think it's an edge attribute, then you see it gets to 0.017, and now we got the correct value for those edge lengths. And let's do so that this is now stored, and I'm going to actually group this. And now that we know the length of each edge, let's just find, for example, the right neighbor. So I'm going to delete the drawings we don't need, and let's find the right neighbor, which is the one here. For that, let's find the nearest point. If we go to the right by this amount, to find the nearest point, let's just search for sample nearest, and I mean, from a geometry, this allows us to find the nearest point at the position. If I use the position itself, of course, it's gonna find, it's gonna run, for example, on this point. This logic here is gonna run on this point. This little program, and it's gonna find at the position of this point the nearest point, which is of course gonna be the same point. But we are not interested in the same point, but we want to move to the right, so we have to add to our position on the x something, and that something is the named attribute, our edge length. So we want to go to the right by the edge length, but not like that. Instead, let's just use a combine x, y, z, because we only want to move on the x-axis. So I'm going to move here, and this one gives our right neighbor. So let's use a store named attribute, plug this here, And then we can store this index that we get from here as an integer attribute, because the index is a whole number, 0, 1, 2, whatever. It is, you know, it's not a number with a decimal point, like you see those numbers here are floats. But if you preview this, for example, you see these are full numbers previewed right here. And we are going to store this as an attribute called right. So this is the right neighbor. And now we are going to store the left neighbor, which is the exact same logic, but instead we are just going to, or actually I'm going to maybe just do like that so that it's a bit more tidy. I'm going to take those, and instead of adding this, I'm going to subtract this on the x so that we end up on the other side. And I'm going to plug this to the sample position, find the index. This is the left one. And now we need the right one, which is again the exact, the up one, which is the same story. I'm going to put the index here, find from this geometry, and I'm going to add on the y-axis so that we get up. This gives us the up neighbor, and I'm going to now just take those things here and move them here so that we have right, left, up, and we find the down. And for finding the down neighbor, we just have to subtract so that we move down. And the neighbors are stored in a much tidier way than I did in my previous node group. What I did for YouTube, so I mean, I learned something new as well, and how to organize things. And the neighbors are stored. Let's call this store neighbors. Store neighbors. Put this in the start here. You can see how much of an effect grouping has. If you would have this massive piece of nodes here, it would make this look like a huge node tree, but actually it's a very compact one still, even though we have quite a lot of nodes already. So we have the neighbors, and as you remember, we would have to find the divergence now. So for the divergence, as you remember, we have to do outflow minus inflow. So we have to do up minus down and left, right minus left neighbors, and find the x component of the velocity at those neighbors. So let's first find the velocity at those neighbors. How do we do this? We need a tool for that, and the tool is called evaluate at index. Evaluate at index, and we are going to take, you know, what is happening here? What is this node even doing? This node is a kind of a the same thing as sample index, the exact same thing. I mean, logic with this internal logic, but the difference is that this node needs a geometry input. So you need to specify from this geometry and from this index, I want to get this value. But what this node does is that it doesn't need the geometry input. So it's going to just take the geometry from the context of how this node is used. And if you're using this on the same object, then doing, you know, operations inside of the same object, it's much more convenient to use this one because you don't have to like plug in different meshes. But the sample index one can be used to get, for example, from a triangle, you want to get something to a cube, but the evaluate at index is if you want to get from the same cube values to the same cube, you know, so that you don't have any different objects or geometries you have to specify. And we want to get from the right neighbor the velocity. Which index? The index that we're going to use is the right neighbor's index. For every point, we get the right neighbor. If you, by the way, preview this, move here, we already have those here. We have right, so for example, for the point 0, point with the index of 0, the right neighbor has the index of 60. And we have all sorts of different numbers here. Up for the point 269, the up neighbor is 270, for example. And let's see how the difference looks like. So if I just preview the velocity, it looks like that. But if I preview at the right neighbor, it moves a bit left. And why does this happen? This happens because you see here we have red things. So for this point, the right neighbor is red. So if I preview the right neighbor, this point will turn red because to the right of this point I have red, like that. This is how this neighbor logic works. It might seem a bit counterintuitive first. If you're, previewing the right neighbor, but the field moves left, like why is this happening? This is happening because of that. And now I'm going to group those nodes here into something useful, a tool, which is for getting a value from a neighbor. So I'm going to call the first one a neighbor with an American spelling, the American way of life. And the attribute I want to get from here is the, I'm going to call this attribute. And I'm going to, the output I'm going to call attribute as well. The UI might be a bit different if you're using an older version of Blender, but I recommend you use 4.0 since this is just better. Unless you have like specific project needs, then I'm gonna tell you if something is so different you have to do this differently in Blender 3.6. But the only difference is repeat zone, I believe. So now we have this group here. I'm gonna call this get vector from neighbor. And this one is a very useful tool that you can get from the right neighbor or something, and we can get from the left neighbor something, we can get from the up, and we can get from down. As you see, this saved us just so much time copying and switching up nodes. We just have the right tool available. So we have to do outflow minus inflow. So this means up minus down. Let's use a vector math node. Let's do up minus down. And let's do right minus left. Right minus left. And as you remember, we had to multiply those with 0.5. So I'm going to take a scale node and multiply with 0.5. Just as it is. And actually we're not interested in the vectors, but we're interested in case of the right and left. These are on the x-axis, so we want to get the x from here, and we want to get the y from here. You can also separate right from the start, but then you would need many separation nodes. So I think it's easier to do the math like that. And as you remember, in the end we have to add them together. So we add the x and the y together. We preview this, and we get a nice divergence field, which, for example, only the x looks like that, and only the y looks like that. And this is the full divergence field. And let's actually store this divergence field as well as a divergence attribute so that we can access this easily and not calculate this monstrum every time. So let's do the divergence attribute called the D. I found that it is more convenient if you name your attributes something very short, because for example the attribute edge length is it has this auto completion here, but it's just easy when you can tap the D and you know you have this attribute. You don't have to do the second click, which might save you some time in the long term. So Ctrl G, let's make a group out of that, and it looks very nice, very nicely organized. I love how this node group looks. And let's go out, no need to add anything, and let's call this calculate divergence so that we know what this node group is actually doing. Calculate divergence, and now we need to, let's see if the divergence is correct. Maybe we did something in the other way around. And as you know, divergence is telling where we have outflow and where we have inflow, or what is our outflow in the case of this vector field, which looks like that. Now, those negative areas should shrink. So let's take a set position, and let's move the grid by the position itself. And of course, let's scale this down a little bit. Let's not use the full thing. And it seems to me that those areas that are black indeed do shrink when we multiply. And I think in the video I made a little bit of a tongue twister or a mistake when I was telling you that you know, those areas shrink because too much is flowing out from these areas. By these areas I actually meant those bright areas, so that from those bright areas too much is flowing into those dark areas. Not that those dark areas are giving away any water. No, they are not. I mean, you can clearly see that we are flowing water into them. So the divergence field is correct for us, but what we have to do now is that we have to correct the velocity by the divergence. Not by the divergence, sorry. We have to calculate the pressure that would satisfy, that would make the divergence to be 0. And I mean, it seems like this could be something like, let's say, just multiplied with -1, divergence multiplied with -1, and that this is the pressure. Actually, it's not, because it is not giving us the, you know, correct gradients, because as you remember later on when we have, I'm just doing a 2D drawing for you right now, I'm going to do this here. Later on when we have, you know, this pressure gradient like that afterwards, for example, we have, you know, vectors from here telling us how the velocity should behave. But if we just find the direct inverse of this divergence, it doesn't work, because in our grid we have a lot of points, and they all like are part of a single system that needs to be balanced. But if you, for example, move, I don't know, this point up, for example, or change the velocity here, then maybe it solves divergence here and here, but it doesn't solve it here and here at all, for example. So you have to like adjust this one, and then you solve the divergence here, but then it kind of, you know, makes an error here. So you have to like increment. And I mean, it is theoretically possible to find the values of this thing at once, but it is a super complex linear equation that has exactly as many unknowns as we have points, which currently we have 3,600 points. So it doesn't, it's not viable to do this, because we would have to like manually put this together, and the computer has to be able to do this for every point count, every case, you know, every liquid simulation case we have. So we just cannot find the absolute correct answer. We have to do this iteratively. And for that, the formula is that we take, for example, this cell here, and we find the average, we calculate the pressure that that balances out the divergence. And for that, we find the average pressure of the neighbor cells, and we subtract a bit of divergence. As you see, the divergence is negative here. So if you have like a -3 as a divergence, and if we subtract that -3, then, you know, it turns into a +3. So we get more pressure here where we have negative divergence, and in the areas of negative divergence, we do have water flowing in from everywhere, basically. So this is how the pressure gets larger in those areas, and in the end helps us. Now, of course, don't listen to me with the idea that I just, you know, figured everything of that out myself. No, of course I didn't. I mean, and I probably wouldn't have guessed how to do this, but I read some papers, I watched some other videos from other Blender creators, and I got this idea from over time, and I can now, you know, replicate this pretty well and understand the principles, but I'm not like a fluid simulation scientist, so just telling that, so maybe I make some mistakes. But let's do this. Let's find the average pressure from my neighbors. First, let's make a guess for the pressure, because we are actually using a Gauss-Seidel, no, it's not Gauss-Seidel. It's an iterative linear solver. Jacobi is the name, I believe. What it does is that, you know, we first make a guess for the pressure. We think, okay, the pressure might be maybe 0. It can be, I don't know, whatever we want. But let's make it 0. Now, I think it might get unstable if you put like, I don't know, -69,000 here. So let's put 0. And now we start to solve the equation iteratively over and over again, and we get the answer. If you want to, you can Google Jacobi's or Gauss-Seidel methods, and you can see it's like pretty wild. So you, for example, have like an equation like 3x plus y equals 4, and you have, I don't know, 2y plus x is 6. Of course, these are just random, and I'm not going to do this true, but in the end, if you just, take the answers and plug them into the consecutive results that you get with some random numbers, it will converge to a certain result. So for example, if the answer is that x is equal to 2, then at the first iteration maybe you get 4, then you get -2, then you get 2.3, then you get 1.99, and in the end it will get you like very close, jumping around this 2. So this is how the equation system solving works. Of course, I'm not a mathematician, so I'm not that good in that. But let's do now so that we find the pressure from my neighbors. For that, we already have a node group that kind of does this, which is get vector from neighbor. But since the pressure is a float number, just like the divergence, it gives us a grayscale map. We actually would need another system which is not get vector from neighbor, but get float from neighbor. And I'm gonna name this that, and I'm gonna switch the attribute inside here for the float, and the type of the attribute to be a float as well. And now I can use this, and from the right neighbor get the pressure, from the left neighbor get the pressure, and of course from the up and down as well. I mean, finding the average is cool in that sense that you don't have to know the order of things. You don't have to like do outflow minus inflow, whatever. You just have to add things together and divide with the amount of the elements, which is 4. This is the classical way of finding the average. For example, if you have I don't know, grades in school, you have 3, you have 1, and you have 5. Then what is your average grade? You add all of them together, which is 3 plus 1 plus 5, which is 4 plus 5 is 9, divided by 3, maybe a better one, divided by 3, and this equals that your average mark at school is 3. This is how it works. So add elements together and divide by the number of them. So let's add them together. I'm using the node wrangler, helpful thing for that. It's Alt, right click, and then you can connect nodes like that. And we added them together, and we just multiply them with 0.5. Sorry, we divide them with 4, since we have 4 elements. Or we can also multiply with 1 divided by 4, which is 0.25. Up to you what you want to do. And now we have to subtract a little bit of divergence. Not too much because it will get unstable. But let's take the divergence and let's subtract it. And of course, not too much, but 1/4 as well. And this is now our pressure. So let's store this as pressure. Doing like that. And I'm going to group this. And I'm going to call this a pressure iteration. So let's call this pressure iteration. Move this about here. And now we have to, if you're using 3.6 for some reason, you have to do like that around, I would say like, I mean, already like a few are okay, but it might still get with higher velocity, it's a bit unstable. So use like, I would recommend like 20 times, but you can use more. And if you're using Blender 4, we can use a repeat zone that allows us to repeat the input of a certain node, input of a certain node group like that. So it does the inside automatically for us 20 times, and it's done. Let's just group all of that once more, and let's maybe connect the iterations here in case we want to change this. Although I find that, you don't actually need to change too much. It works, 20 is okay. Let's call this calculate pressure. And we missed the capital here so that it's all nice and tidy. And let's drag all the end here closer. A very neat and tidy node group we have here. And let's see how our pressure looks like. And divergence and pressure. So the pressure looks like that, divergence like that. As you see, while they are the inverses of each other, they still have a little bit of a difference. So for example, if I do just one iteration of pressure, I mean, this one is pretty much the inverse of the divergence. But if I add more iterations, you see it gets different. It gets like smoother over time, but obviously adding as many iterations is a bit too much, and it doesn't help. It will make your simulation a bit flickery, like shaky a little bit. Don't add too much, because this is actually one of the easiest ways for calculating the pressure. We have other things. We have, you know, Jacobi method. We have a thing called multigrids. It's multigrids, which is like it's basically selecting like checkerboard tiles 1/1 and doing the calculations with them and then switching it up. And we have, you know, a whole lot of very cool scientists around the world thinking about new ways to do this. But this is the easiest one, and I think the most understandable one. Although this is the one area of fluid simulations which I don't understand fully, maybe 80%. But now we have the pressure. And this pressure, if we use this as the displacement of our I'm just, you know, looking for nodes that even don't exist. Set position. If I plug this into the offset, it will of course offset this on every axis here in this direction, but we only want to do this on the z direction. I'm going to put this to the z, and now you see we have this little displacement here going on that tells us, okay, here we have lower pressure and here we have higher pressure. This is how it works. And we need to find now the vectors that go up the pressure. So we need to understand, like, where is the pressure directed towards? You know, arrows on the surface of this pressure here that go up this slope and tell me how is the pressure changing over time, which is, I think, the derivative of the pressure field. But you know, the derivative of a function like that, for example, is this straight tangent line over here. Tangent is like the touching straight line of this function. And we need to find the direction vector of this field. How do we find this? This is a good question. Well, if you want to know, for example, the derivative of this field, then what you would do, and also the animation on YouTube showed this very well, have the x-axis, have the y-axis, then, you just, find the value here, okay, of this function, and find the value here. And, I mean, this approximates, if you now draw this, no, I just can't. If you now draw the line through those 2 points, it is kind of the tangent line of this function. And the closer and closer you put those, the more correct result you get. We cannot make them go closer and closer. The closest we can go is the distance of those 2 points that luckily happen to be our neighbors. So we already have access to those points. We just need to know the value of those, of the pressure field here. Now, if you are, in a pure mathematical field, calculating the derivative is a bit different, and you can find, I believe it's called a closed form solution, which means that, if you have a formula like x squared, which is the kind of a function like that, just a parabola, then, you can find, for example, the derivative of this, which is written like that, and this is 2x. I'm not going to delve into the rules right now, but this, 2x is a linear equation, which happens to be just the line here, so that you can, always find the correct thing. But our pressure field is not an easy equation like this x squared here. It is something much more complex, and it is discrete, which means that we have, we don't have like a pure continuous mathematical sine wave. We actually have, different points like pixels for this function. So we cannot use any any systems like those math things. Maybe you remember them from high school, I suppose. And if you want to find that thing, then as you see, we have to find 2 different points. So we find it, on the x-axis, we find how much it changes. On the y-axis, how much it changes, and we put this together into a vector. Nothing more complicated. So let's take a float curve. Sorry, float from neighbor, get float from neighbor. And let's do on the x-axis first, right and left. And I want to get not the velocity, but the pressure and the pressure. And now, of course, on the up and down as well. So let's do up and down. And, we are going to subtract them in one order that we decide. And it's not important if it's left minus right, like outflow minus inflow or inflow minus outflow, but they have to be, consistent between those 2 groups. So if it is outflow minus inflow on the x, it has to be the same on the y as well. And since we've been doing everything on outflow minus inflow so far, let's do it here as well for the clarity. If you do this the other way around, you just get vectors in a different direction. The same vector, of course, but just a different direction. You can multiply this with -1 to get the correct thing back. And we're going to do right minus left, outflow minus inflow, outflow minus inflow. And as you remember, we have to divide with 2 or multiply with 0.5. And now we have 2 things that look like that. This shows how the pressure changes in the x direction. And if you see, this is all the minus x sides of the slopes are bright, because it tells us, if you start coming from here, we go up, and here we go down because it's negative. This is what the values show us. It is, it's very real life. There is nothing, I know that derivative might sound like woo, like some very theoretical and horrible mathematical things, but actually, I think this visualization makes it very clear, and we can see the same thing with y, so that we can see, okay, I'm coming up from this direction, and then I'm be going down in the other direction, which is pretty clear. And we will be just combining them into a vector. So up and down are for the y, and left and right are for the x. And now if we preview this, you can see we have a vector field. And I'm going to show that this vector field is not just a gimmick, but it is actually a true thing that works. If I instance some points here, and I'm going to join those together actually. Well, I'm just going to, put those just for the output for a moment. Basically, what I'm going to do is I'm going to instance some mesh lines on those points, and I'm going to make them point in the direction of those vectors. So if I preview them here, you can see, some lines. And now if I align the rotation of them to this vector, you can see that they look like that. Of course, I have to turn off the displacement, or I'm going to just make it very weak so that you can see how this is working. And I think they are a bit too long, so I'm going to make 0.05 maybe. Doesn't seem, yeah, it does work, but it just displacement is kind of ruining the thing. So now you can see this. At least the idea that these 2 represent the field, you can see that they're going away from those little slopes, as you can see. So our vector field is indeed giving us the right values. And now that we have this vector field, we have to just subtract this from our velocity. Since if we have I'm going to delete the pressure displacements here, so that we have a tidier field. So if we have like a high pressure field, and we have a vector going up and the velocity going here as well, if you subtract this velocity from that, then it will turn back or become 0 if they have the same length, and this will nudge the field to be much more like a fluid. not to go into those pressurized areas. So I'm going to store a new velocity field that is made of the velocity of which the pressure velocity has been subtracted. I'm going to do vector subtract and like that. And I'm going to connect this into the velocity and select all those nodes, plug them into their own group and call this correct velocity. Not the velocity, but velocity. And our velocity should work, at least in theory, as a fluid, although surprises can happen all the time. So let us see. And it's working nicely. If I turn this off, you see we have divergence. So it is working very nicely and acting like a fluid. I mean, you can kind of intuitively feel it feels like a fluid, but of course you can't see this because it doesn't look exactly like that. So let's add those points on the surface of this fluid right now. If the points move by the velocity of the fluid, it will give us a very fluid-like surface, and it will look very cool and allow us to visualize what is actually happening here. So let's add some points, and for that I'm going to call my object first fluid so that it is clear, not to have like a massive outliner with 1,000 objects called cube 0001. Right now this is correct.blend, something like that. I don't want to have this. And I'm going to call this geometry node setup also a fluid, maybe even fluid simulation. You're going to, by the way, you can get this file from the same folder that you have this tutorial in. And I'm going to just add another object. I mean, we can add those points as part of this simulation, which could work, but I feel it gets a little bit complicated and cumbersome actually. Not just for the sake of the tutorial, but actually in production, I would not add the point simulation into this simulation because you know, we would have like different lanes going on here, which we could do, like, you know, and we have, you know, some points here and maybe some other things up there, but I feel it gets a bit, you know, you might have some timing issues and so on. So let's do, you know, like that. We have a saying in Estonia that every carpenter should stay at its own wood. So this kind of means that every simulation has to, you know, serve its own purpose. And let's add a new object called plane. I'm going to call this one points. Add a new set of geometry nodes. Call this moving points. And we don't need the plane itself. I'm just going to take in the fluid. And I'm going to turn this into a... you know, now we have the same fluid object inside here. So if I now take the fluid object and I move this, sorry, the points object, and I move this, you can see we have the fluid object copied. And on the surface here, I mean, it is the same object, we get all the attributes, but it's just a fresh copy that we can do things with. For example, we can distribute some points on the faces here, like let's say 1,000 points. And they don't move currently because we haven't told them to move. So let's make them move. And you already know that we want to make a simulation. So let's just, you know, let's get this out of the way. Let's add a simulation zone here. And let's drag the points into the geometry like that. And it seems that nothing should happen, which is true. Nothing happens, but we get this pink line here that tells us that the simulation has been baked. If you change something, it turns dashed, which means something has changed. Please rebake the simulation. I'm gonna take the set position node because we want to move the points, and if I put something like 1 millimeter here, then it's gonna move every frame 1 millimeter, which is like, I don't know how much this is in inches, but you can see that it's not a lot. But we need to move them not by this 1 millimeter, but by the velocity of the fluid. So let's take, well, what do we take? An intuitive way would be to just take the named attribute and take the velocity here. And since we are using this as our simulation input, we can use all the attributes. I'm going to put this into the offset and it moves away very fast. much faster than the fluid itself moved. So the reason for that is the time step problems, because in the fluid simulation, I can show you. In the fluid simulation, we store the velocity, which is quite fast, you know, we don't slow it down in any ways. And then, not in the time step, but in the advection, we move the velocity by a slowed down velocity, but we don't slow the actual velocity that we get, you know. The same velocity is gonna get stored. And in the end here, we still get out the quite fast velocity, and it's gonna be used in the points simulation without any slowdown as well. So let's take the store. Well, actually, we don't have to store the time step again. Where is it? Where is it? Time step? It's just time step. So we don't have to store this again. I mean, actually, there are 3 ways to do this. We could do like that, which is useless because we don't need to store the time step on every frame. It's going to be the same during the whole animation. A wiser thing would be to do this here, but still we don't need this because we can get the attributes from the fluid. And since the attribute time step doesn't change over time, we can just use this as it is. And we can vector math, again, scale down the velocity by the delta time. And now the points should move much better, and they do, but it doesn't look like a fluid. And I think if you look at a certain point very closely, for example this one, you see it moves in a straight line all the time. And that's because the velocity that we get from here, it is not changing. It is not changing. It might look as it is, but if I don't move, you see the fluid velocity is changing. For example, if I look here, you see the fluid's velocity is changing, but the point one that I preview here, for some reason isn't. I turned this one off. Okay. But the point velocity, it's not changing. And that's because simulation nodes work so that it takes in the points at the first frame, or doesn't have to be the first. Yeah, it kind of is the first frame of simulation all the time. Reads in the data and then repeats and repeats and repeats this every frame. And then in the end, you do something as well. This is also executed once. But you know, if it starts, you know, repeat on second and third frame, it doesn't take into account what is happening here anymore. So if I, for example, you know, play this, I want to just put 1 point here. You see, at the first frame I can change this and the point count changes. But if I now play the animation and I now change this, it doesn't change anymore. Because what is read in at the first frame is going to be kept here, and the only changes that we do can be done here. So it is, I think, wise that we just scrap this and we add the points here. But we still don't get anything. And we also get a problem. The problem is that the input geometry is unsupported. And it is because at the first frame, we take in the fluid mesh. As you see, it's the mesh object of the fluid. I'm going to hide the fluid object for a moment so that, you know, we take it in, you know, the mesh, we distribute some points on it. And then we, at the next frame, we put the points back into the start. We run this again, and we want to distribute some points on them, but we cannot, because this node can't distribute points on points. It can only do this so on meshes, but we've lost our mesh. So what we should do, we should build like a little alternative way for this mesh that comes in, you know, kind of like make a copy of it, and we just, you know, pass this through all the time so that we actually don't do anything with it, but we just keep this with us so that we can distribute some points on it. And for that, we have to make a difference in the geometry. We have to separate it based on the content. And for that, we have a node called separate components. I'm going to put this here. And this allows us to make a difference between those different geometry types. And currently we're interested in the point cloud and the mesh. So we want to distribute on the mesh and we want to move the point cloud. And of course you have to join them together in the end as well, because otherwise we just wouldn't be able to see anything. It would get lost on the way. So let's play again. And I'm going to delete what I did here and all those keyframes as well. We still don't get anything, and that's because we don't have any meshes. Because at the first frame, take the mesh in, distribute some points, but we don't pass this mesh on. We should be passing this on. And now if you play this, well, we still don't get anything, but let's move the points. And now you see, oh, this looks pretty nice. And we get some added points. Although I think that the radius should be much smaller so that we can actually get a nicer scene out of it. So I'm gonna put like maybe 3 millimeters for the point radius. And you see, okay, but doesn't look too much like liquid though. They are all having the same velocity. True, very true. That's because, as you remember, we take in the velocity of the first frame of the fluid object that it inherits. When you distribute, it inherits the velocity, but we are not refreshing the velocity. So this might simulate, you know, how much it wants, but we just don't get this data in anymore after the first frame. So we should read this in artificially. And for that, let's use a, well, if you have a point appearing somewhere, like for example, I'm going to look for a nice here. Then it gets the velocity from here, which is the average velocity of those points. A weighted average, like, you know, more from the point where it's closer to, less from the one where it's further away. And now when it moves here, it should read in from here again. And then it gets here, it should read in from here, from those points again. From the face, it's on. And for that, we have a node we have already used, which is sample nearest surface. And whatever we do here, we can just sample this on each frame from the fluid object. So it finds the nearest face, the face it is the closest to, and then samples from it. So I'm gonna group this, and I'm gonna call this move points by velocity. Gonna put this here, much more tidy, and let's play this and to see, okay, this is now much more like a liquid though. This is much more like a liquid. I'm gonna add some more speed to my liquid because I feel it might be a little bit too slow. Okay, this is now much better. You see those curling things here, and this looks very nice. But unless you like those lines, which can be cool in a certain scenario, for example, when you add a larger density of those, like that, it can be cool. But we are interested in, you know, more of a sand-like behavior, so we want to like get the fluid field like that moves on forever and forever. And for that, we should change seed on every frame, because currently they are added, you know, every frame is going to be added into the same place, as you see. They're going to get moved, but they're going to be added at the same place, to the same place. So let's add a scene time node, and let's put the frame into the seed. And now they are added very randomly on each frame, which is cool, which is giving us those really nice fluid-like behavior. And the next issue that is separating us from a nice scene is that the points move across, move over the border, and then they start to move with this only one single direction. That's because the sample, the nearest surface is always, you know, here. Whether they are here or here or here, it's still going to be the same nearest surface. And we don't need those points because they are not useful for us anymore. They just are performance hogs, or I don't know if this is the right word, but they just, you know, eat our CPU power. So let's delete those points. So I'm going to put the deletion not at the new points, because if I would delete here, this would only stop new points being added outside of the border, which doesn't make sense because they're not going to be added there anyways. I'm going to put this here when we have the point cloud, and not just everywhere, but before I move them, because movement, I'm going to see if the timing shows that. You know, this takes like currently like 0.40 milliseconds, but let's say I have like 100,000 points. Of course it deletes, yeah, sure. Then you see it takes like 36 milliseconds already, but if I delete the rest before, I can save on performance. So let's go to the first frame, let's add like 1,000 points back. And when should we delete them? We should delete them if they are over the border. We can do like a more complex setup where it takes into account the shape of your grid, but the grid is always going to be a rectangular shape, so we can actually make this in a much simpler and cheaper way. So if we know the position of those points, we can just separate this. So separate x, y, z, x, y, and z. X and y are what we're interested in, and we can compare, you know, on the x, is it larger than 0.5 in this case? And then we have to do, is it less than, you know, minus 0.5 and so on. But there is a faster operation for that, which is the equal. So we can compare, is this equal to 0 with the threshold? Right, like that. And we can, we want inverse, so we can use a not equal. So if they are not equal with this threshold, remove them. And let's do the same thing for the y-axis. Looks like that. And to combine them, we have to use a Boolean math node, which is not set to AND, because AND means wherever those two things are true, which only happens down here. When those two things are true at the same time, we have to put OR. So either one of them can be true, and we remove those edges. Now I'm going to take them, move them here, and delete the geometry. So now if you play this, nothing goes over the border, it's going to get cut off. Awesome. And I'm going to group those, and let's call this delete if out of bounds. If you would like to, you could also add like a threshold controller for here, so that you can control the amount being deleted, but it's fine for now. I think you know how to do this. And now we have the fluid here, but let's see if the performance is, getting slower. And yes, it is, because we are adding more and more and more points, so the FPS keeps dropping until probably Blender crashes or your memory is full, already 5 gigabytes used. Let me see. At the first frame is 200 megabytes, but you see if you play this, it constantly gets larger. So how can we solve this? Let's do so that, we for example, we remove the points if they get older than something, like for example, older than 50 frames. If the point has been existing more, we remove this. So for that, we need some kind of a number on each point that tells us how much it has been existing. So for that, let's do so that if the point exists, on each frame, we add 1 to the age of the point. So for that, we need an attribute called age. I'm going to take a store named attribute, a variable, and it's can be, I think, an integer. Yeah, let's make it an integer, because I think it saves memory if this is a float or an integer. With this simulation, it already matters, because when I made the thumbnail, for example, at a certain point, my RAM was like 50 gigabytes of my RAM was used, which was like, I wasn't expecting this to happen. So really, optimizing here and there can add up, whether or not you can visualize your animation. So let's do so that we store an attribute called age, and at each frame, the attribute age should be the attribute age from the last frame plus 1. So let's get the attribute called age. It doesn't give us this right now because of this logic here, but we just add this here, and now we add 1 to it. So on every frame, it adds 1 to itself. Let's group this, and let's call this crate age, great age, middle age, whatever. And now if you play this, I mean, we just get the age attribute, which is gonna play this, for example. Let's see, point. Where is the, you know, the age attributes? Some of them have the value of 0, but some of those are 23 years old. Some of those have the same age as I am, which is 22, and some of them have 47, kind of middle age already. So we should delete them. I mean, so which is the age after which the point is no more useful? Retirement, 66. Okay, let's delete them after 66, which actually happens to be the retirement age in Estonia, I believe. Anyways, let's delete the geometry. If the age is larger than 66, which is kind of a dystopian way of managing the society, but we're gonna do this. So if the age is larger than 66, delete. And now we should have the same performance all the time. A stable, okay, the memory is still increasing, and that's because we have, you know, different frames, of course, but it's not going up so fast. But the performance is always the same. But we have this flickery behavior here. This is the next thing we are going to solve. You know, those retirement happens too fast, and they just disappear like a Thanos snap, you know. So I'm going to first group this one and call this delete if over age. And then we should do something about their, you know, flickering here, because it happens, you know, it doesn't look very good. So how do we solve this? Well, first, if you want to solve something like that, you should think what would be the ideal end result. And what I think would be is, instead of those points like, you know, appearing, disappearing, it should be more like that. How can we do this? Well, first let's think, like, what is this thing even representing? This is representing, I mean, what am I drawing here? I'm drawing here the radius of the point dependent to the age of the point. So I want, you know, the point to be, to start, I want the age to affect the radius of the point. Okay, so set point radius could be our helper, and we can do that, you know, that the points appear very small and they become smaller, bigger afterwards. So this would be like that, or more like that, you know, big points appear, and once they get to the down pipe here, they get smaller. But we want this to be dynamic, so we would instead want to change this. So let's make it so that we map the age to, where is it? It's lost somewhere. Okay, so that we map the age, the whole age of the point, which is currently delete if over age. I'm gonna add a controller here, and I'm gonna call this age max. If the, you know, currently it's 66, but let's map this to the range of 0 to 1, so that it is like the life cycle of a point from 0 to 1. 0 is the birth, 1 is the death, and we want to do some decisions based on that. So let's take a map range, and let's take the named attribute, which is the age, and plug this here. If you don't get this age attribute, you can just type it in if you know it exists and put integer here, it's gonna work. I want to map the age from minimum 0, which is the minimum, but the from max can change depending on the age max here. So I'm going to store this one as well as a named attribute, which is, you know, a bit memory hog, a bit of a memory, you know, uses a bit of memory, but I think it's just convenient if this is stored as an age max. And now I can take an attribute called age max, and I can max map like that. So age from 0 to max will be 0 to 1. And I'm going to preview this and show you how it works. So you see, you know, these points have now the younger points are darker and the older points are glowing in their best years. And we want to affect the radius with this. So if I would just to put this here, they would be very large. And that's because this is, you know, radius from 0 to 1 meter, which is a bit too much. So I'm going to multiply this radius with something that is more reasonable. Like that, 0.01 for example. And now see, you know, when they appear, their age is getting larger, and for example here, you see they get larger. And also at the first frame, they should be probably 0 because the new points are flickering. So I'm going to put this to 0. And now see, this is what they do. But instead of being like that, we should map the range to be not 0 and 1, but after it should be also 0. So for that is a very good node we can use, which is a float curve, which works in the range of 0 to 1, which is the reason we did this mapping. And we can do so that this is at 0, the point should be 0, at middle age something else, and at death also 0. Let's put here 0.1, and now it should work splendidly, which is exactly how it works. I mean, you can see some, you know, waving and some blobbing and some bubbling there, but it's much better than what we had before, where we had, you know, just this flickering binary visibility. So let's put this all into one group, and let's add a radius controller here. And I'm gonna add, you know, I'm gonna divide the number that we input here with 10 so that it's easier to slide with our mouse. I'm gonna call this radius, like that. And now if I put here 1, it will be super large, but I'm going to put here 0.1 and 0.01. Actually, I even think the divisions should be like 100 maybe, so that, you know, so that you can more easily slide with your mouse here and get some reasonable results. And this looks awesome. This is like a real nice fluid field. However, it is good, and this is how we ended the last tutorial. Although we had some colors as well here, but we're going to add them in a minute. No, not the last tutorial, but the YouTube one. We're going to add them in a minute, but what we're going to also do is that we're going to add some obstacles, which are easy to add, and they can add a lot to your scene. So let's add a random object in the center here. There's like I don't know, an icosphere. I'm just gonna add a bit more subdivisions for it, and I'm gonna make it smaller. So I'm gonna make this an obstacle, and the fluid should ideally, you know, conform itself to this and move around it. And for that, if I want to, you know, what is an obstacle? If there is a wall, and there is a ball that is, you know, being thrown into the wall, then the velocity is something, and when it hits the wall, then the velocity will be 0. This is how an obstacle works, because an obstacle is actually an object that turns your speed into 0. I mean, otherwise it wouldn't be an obstacle. For example, you don't call air an obstacle because it doesn't have a massive effect on your speed. If, for example, you're doing rocket science, the air is very well an obstacle because there it plays a pretty big role of all the calculations and stuff. But in real life, you know, if you're going to the shop, you don't, I mean, talk about, you might talk about, you know, a wall that has been built in front of the shop as an obstacle, but not the air, because it doesn't change your velocity. So knowing that we want to change the velocity, let's take the fluid object, and I'm just gonna let you think for a moment how you would add obstacles. And I think you know this. We would just have to make the velocity 0, but not everywhere, but inside of this ball. Okay, so the velocity must be 0, inside of this ball. How do we select the inside of this ball? Many ways to do this. Complicated ways, easier ways. One of the easiest ways is actually, I have my own node group for that, which is find inside, which I use quite a lot, and I don't want to build this every time. I mark this as an asset. Is this? Yeah, I mark this as an asset so that I can use this. And internally it looks like that. What it does is that it shoots some rays down from the ball. Why don't I see the inside? Shoot some rays down, and if they, hit the plane, what happens then is that we get the normal of the plane, which is pointing up. And if the normal of the ball itself at this location is also pointing in the same direction, this means we have found what is inside of the sphere. So this is how it works, exactly like that. And I'm going to take the icosphere. Sorry, I'm actually going to, I'm going to take the icosphere and I'm going to put this as the selection. And now if I preview this, for some reason I don't see anything, which is a bit weird. Because of course my fluid cannot be seen. And we see the inside has been marked white. So now currently in only these locations we store the velocity to be 0. So if we preview the velocity before before this, we see it's like that. And if you preview after, we've turned it into a 0. Should work well. And I'm going to group this like that. And I'm going to call this set obstacles. But you probably see that it's not a very good node group because the obstacle is always the same. I mean, I put this node group somewhere, and the obstacle, it's always referencing the icosphere, which is not good. It shouldn't do that because maybe you don't have this icosphere in your scene and you want to specify your own object. Then we can do like that, so that we can, outside select the object. But what if we had 7 things we want to use as obstacles? Do we have to join them into one object? Of course not. So let's do instead so that we add a collection called the obstacles. And inside of this collection, I'm going to move the icosphere like that. I'm going to remove this and I'm going to drag the collection inside. Set this to relative, and because I want to get the actual position of those objects, not all of these objects in a... Well, actually the relative just works. I have to look at the difference myself too, but relative is working. And I'm going to plug this here, but the problem is collections are imported as instances in Blender, and instances are they're kind of a memory efficient copies of the same object. For example, if you have a ball, you create like instances of it, these all reference back to the same data. So if you change this data, something here, you add like a little lump or on the side here, then all of those will have the same thing as well, which is sometimes what you want. For example, if you're instancing grass on a field, you want to have instances, you want to have the same grass plates. It's very memory efficient. But if you're doing some kind of calculations, we need to have, like we do here with raycast, it tells us that it cannot use instances. And this is logical because it needs to have real geometry in every different location. So we're going to just add a realize instances in between here. And now we can add this obstacles collection here. And this is how it works. Now we can define different collections or not use them at all. And let's delete this and let's see what the points do. So you see they do seem to respect because they don't move in the inside, but we should make this a bit more visible because let's for example add like a little push to this velocity. So let's take an add node and in which direction do you want to add. Let's make it so that we have velocity coming down like that. So this would be minus velocity on the y-axis. And now it moves like that, and you see the velocity and these objects, the obstacles work really well, and the points stop and don't move anymore. But if you have a faster kind of velocity, like maybe like that, then you see, okay, there is something weird happening here, because the points are moving inside of this obstacle, and this shouldn't really happen. And this happens because of the time step issues. So physics simulations are discrete in computers, which means, I mean, actually I wonder if they're discrete in real life as well, but I'm gonna first explain to you and then we can think about this. So if you have a ball in the air, and in physics simulations we give them velocity, then on the next frame we move it here, then we calculate the new velocity and so on. So this is how it would work. So while the movement of the ball can be mathematically, you know, given with a parabola formula like that, where you can find the ball at any case, then in physics simulations we can't use this. We are using a discrete time step. And in real life, the time steps are, of course, very small. You have those, you know, atomic level of movement. And I wonder actually, because the smallest distance in real life in our world is the Planck constant, which is something really small, like, you know, minus, I don't know, it should be like 10 minus 26th power of a meter or something. I'm not really sure about the number, but it's very small. So I wonder if actually real life is also discrete, because if this is the smallest distance a particle can travel in you know, in a quantum world, then this means we actually, does this mean we have time steps because an object moves like that by the Planck constant? I don't know, just something to think about. But since we have the time steps, you know, currently we have 5 time steps, but let's say we only had 2, then we would get something like that. But let's say we only have 1, then we would get maybe something very inexact, something that is not precise at all. And maybe if you would have much you know, smaller time steps, we would have a much better result, because we can account for some wind forces, for example. So the ball would maybe move like that if you had smaller time steps. So it depends on the resolution of your simulation kind. And currently we don't, I mean, we have 1 time step per 1 frame. We're doing this all once per 1 frame. And if you know, look at the point, for example, it might come like that, then it is here, and it's, oh, that's a problem, but it doesn't have time to change, so it wants to do kind of like that. So if you were to increment with, you know, smaller time steps, it would have the time to turn around and act like a fluid. So to do this, it is super simple actually. We just need to do the same thing twice per frame. So let's take a repeat zone here, and let's do like that. So let's put everything we have inside of 1 big massive repeat zone. Let's do this, and let's put this in the end here. And now we have a repeat zone inside of a simulation zone. That's some advanced stuff, right? We have some purple, we have some brown, looking awesome. And if you do this, I mean, this doesn't change anything. This is just once per frame. But if you were to do this twice per frame, you see it would get twice as fast. And if you do like 8 times per frame, well, it doesn't seem to get faster actually, but just a bit weird. And the reason is that, I mean, if we have the current velocity, we do this once per frame, then as you remember, if we do this twice, we would have to slow down the velocity by 50%, or divide with 2 if we do this 3 times per frame, then by 3, and so on and so on. So this is how it should work. And for that, let's add another thing into our time step that is accounting for that. So if the iterations is 2, then time step should be twice as small. So I'm going to do so that I'm going to multiply the time step with 1 divided by the iteration count. And actually, maybe this should be, I'm going to call this the iterations. Could be called substeps actually. Let's call this substeps, and let's insert this new system. I don't like this too much, but now we can do this like that. So that the time step is gonna be, if you have one substep, it's gonna be 1 divided by 1 times the thing. It's okay. If you have 2 substeps, it's gonna be half of the time step and so on. So we currently have 2 iterations, so let's put it here. We can also add a driver so that we copy as new driver and paste driver, so that now when we change this, they are always the same. So if you put here 1, you see they're clashing into here. If you put here 2, you see they are already, you know, they are much more taking this into account. But actually I'm going to remove the noise for a moment from here. I'm just going to use this downward velocity, and you see, okay, but it's also slowing down. And that's because, you know, the velocity balances out, and since we're not adding any more new energy into the simulation, we were doing this before the simulation, it kind of slows down because we're not adding any more. So let's add more, but I mean, obviously we cannot just, I'm just gonna put them like that because we shouldn't be thinking about repeat zones anymore. Our whole simulation is like in here now. I mean, if we are just doing like that, then of course it doesn't work, because we are, whatever we are simulating, we're just rewriting the whole velocity, and this is not good. So we should do so that we only, for example, add like a little inflow zone up here, and here we constantly add velocity, and the whole simulation down here can be simulated very well. And for that, what we can do is, again with the selection, we can just write the velocity into this area only. And for that, I'm going to add an inflow object. I'm going to make this smaller, much smaller, and I'm going to move this here, so that, let's do so that what's inside of this object is going to be our inflow. And you already know how to do this. We just have to take in the object. You have to use the find inside a node group, and once you know, it's the same thing with those raycasts, and if you know what's inside, we're gonna make the velocity be that. And I'm gonna group this, and I'm gonna call this add custom velocity, or I can call this inflow, whatever you like. I'm gonna call this inflow. And now inside of this cube, I'm going to use some velocity. Of course, I'm going to turn off anything that we have before. And sometimes it might get a little bit weird and not work. But let's see what our inflow velocity actually is. I mean, I connect this here so that I can change this, and I'm going to call this velocity, and subtype can also be velocity. And now it has those meters per second added for convenience. And let's do it in the direction of this ball, so -1 meter per second, which is a bit weird that it actually doesn't work. Okay, I found the reason why it's not working, and the reason is that we forgot the relative here. So if you are using the original, it's actually using the cube that large, so it's like writing the whole velocity all the time here, which is pretty much the same as without the selection. But if you use the relative, it gets into this smaller cube here, and we can turn it off now, and it should work just fantastically right, which it does, works super well. You also have some fluid, you know, vortices happening here. It's pretty good. And you know, the faster the velocity is going to be, Of course, the more you might need time steps, but I think this is okay. If you add too much, your performance is gonna be lost. And the last thing before we sign off from here is, if I now move this object, I mean, if I move this object, you see, it works in the sense that it kind of stops the fluid flow, but it is, if I do like that, it's not moving it up, it's not moving the fluid. So let's do so that it actually moves the fluid with itself, which is quite cool, can get some quite cool effects with it. And we have the inflow here, but let's do move, how to call this, move a velocity with the object. So essentially what we should do is that we should move the velocity so that if you move it from here to there, for example, the velocity that is stored inside of this object, it should be called, it should be the velocity of the object itself, so that this makes the field move. Let's do this. Let's add a store named attribute, because we want to change our velocity into something else, not to 0, because this means it doesn't move anymore. Now it moves, no it doesn't. And let's find the inside of the object first. So inside of the, not of the cube, but inside of the icosphere. And actually it's not good if the same object is the obstacle. So let's actually do so that we add a different copy and we move it to another called stir objects, so that we can mix the liquid with this object. And I'm gonna just call it stir, not stree, but stir. And I'm gonna make it smaller as well. So now I can take the stir object and put it inside. And if I know the inside, I can put the velocity to be 0 there. Now this is exactly the same thing as doing an obstacle, but instead I should have the velocity of this object inside here. Okay, now it's only for us to find the velocity of the stir object, which is, I ran into some problems in the meantime, so that's why there is like a harsh cut here, might be. But yep, now I have everything cleared up. And to find the location of, or the velocity of this object, we need to know what is the, we need to know, velocity needs at least 2 moments in time. It needs, I mean, you can't say the velocity of an object just looking at an image. You can guess that things are fast or not based on the consequences, but you don't know the exact velocity. But if you know that a ball was at the time 0 in a position 0, and the same ball is at time 1 in position 1, then you know that, okay, I can calculate the velocity, which is current position minus last position, and I can get the velocity. So current position minus last position. So we need to get the current and last position of this object, and I mean the location is pretty easy to get. The current one, we can just view the here. I mean it's that. This is the current location, and let's store this. Let's store this as a vector called stir current, and let's put the location here, store this attribute, and now watch this. If you want to know the last position of this object, we have to store this somewhere as well. But think about this, when the frames come in, the object moves, and we store its position, then we do all the rest here, all the rest, and then we get back to the start and start to go again. We do all those nodes, calculate this, this, and this. We get here. Before we get here, what we do is actually, a new frame has already started. So this object has potentially moved into a new location. But this node here still has stored the old position. So the stir current is currently actually the old position. So before we write the new stir current, I'm going to make a stir previous, new stir previous, that is the stir current. So you can play this through on a paper. Takes a little bit of time, maybe you get this right away. For me, actually, just right now before, that's why I made the cut. I just messed up for some reason. Maybe that's because I've been recording like 2 hours of a tutorial. But yep, this is how it works. And now we get the previous and the current position. So if I take a stir prev and stir current, and I play and why can't I move this? Play and do like that, and the preview. These positions might be, or I mean, because of this, they might not. Yeah, okay. So for some reason, they actually don't seem to be different. Okay, guys, I found the error. Turns out I wasn't stupid. Blender wasn't bugging. Why those two things look the exact same, although inside here they look different, is that we are using a repeat zone. So actually we are doing this twice. And since the object itself isn't moving twice per frame, it's ruining this. So we should do this outside of the repeat zone for it to work. Well, that was a thing to figure out. So let's just do the calculation outside. So I'm gonna do like that. I'm gonna move the two store named attributes out, disconnect this, move them together, and I'm gonna move this just before the repeat zone. So I'm gonna take the stir current, plug them like that, stir prev and current, and now it should work splendidly. I am pretty sure about that. So let's go to the first frame, just in case. Let's turn off a node to reset the simulation. Play this. Okay, let's go to the first frame. So the current, previous. Okay, this works now. This is nice. And based on those, I'm going to group them. We can calculate the velocity. So sorry, we can calculate the velocity, which is called the stir V, stir velocity, which is stir current, and stir previous. And we have to get, the velocity, as you remember, is current minus previous. So we do subtract current minus previous, move them here, and this is exactly how the velocity works. Let's call this stir velocity and plug this here, stir previous and current, and now let's see if this actually works and how does the velocity look like. I'm going to take the stir V and I'm going to remove the keyframes of this object so that I can move this around freely, and you see velocity is 0 because I'm standing. I'm moving up, it's getting green, right, and all that. So it's working nicely. And now we just need to, where the stir object is, we need to put this inside, so switch the velocity for the stir velocity there, and this will give us a cool effect so that we can move the liquid and points around like if we had a spoon or something. So where the stir object is, I want to put the stir velocity. Now this might flop, but let's see how it works. Okay. I'm gonna turn off set obstacles because I don't want this right now. Now, why isn't this working very well? If I, well, okay. If I move here, I mean, you can see it faintly works. You can see some movement because of this ball, but it's very, very weak. And that's because in the advection here, we scale the velocity to be smaller, to be, 1/60th of the velocity, because we have to, we enter the velocity, for example, here we put I don't know, we put 1 meter per second or minus 1 meter per second, and this is per 60 frames in this frame rate, so we have to make this 60 times smaller. However, the store velocity we calculate during the last frame and the next and the current frame, so it is not meters per second but meters per frame, so we need to make this meters per second as well. So let's scale this and let's make this larger by the delta t. So delta t is here, and if we do like that, it's going to be even weaker, but we have to make the inverse. So 1 divided by the time step, which gives us 60. So this is 60 times stronger now, because I mean, if it moves one frame like that, then per 1 second it's going to be 60 times the same distance, which makes sense. And now it should be much better. Yeah, much better is the word I was looking for. It works now. You can stir around, you can move this, and I'm going to turn off the custom velocity for a moment, and I'm going to play this. So it is crazy, isn't it, that you've made a liquid simulation that actually when you move, you see the liquid is squeezing away between those two objects, which is awesome. I mean, how can... This is pure logic, just pure programming and logic. This is honestly fantastic that we can do things like that. Think about this, like 50 years ago, you had computers which were way too weak to do anything like that. Now you can do this on pretty much any computer. Watch this in real time. Use nodes, not some graphic, not some, I don't know, headless command line programming. It is wild how the world has gone like forward at fast pace. And let's group this. Let's call this set stir velocity. Stir has to be the, well, I can use notes, but I can't write. And this is the whole setup here. You can of course group this, make it even more reusable. I made my own fluid simulation node with the same technique. And I hope you learned something from here. I hope you like this extended tutorial. And and I just hit my hand not through the table, but against the table. And anyways, I hope you enjoyed this, and we'll see in the next one. We'll see when the course launches. Ciao.